Suppose you observe 3 customers buying the same products from the same store. The first customer buys 3 cartons of milk, 1 box of eggs, and 2 bags of flour. In total, he pays $26. The second customer picks up 6 cartons of milk, 4 boxes of eggs, and 5 bags of flour. He pays $62. The last customer purchases 3 cartons of milk, 5 boxes of eggs, and 6 bags of flour. His payment amounts to $54. How much do 1 carton of milk, 1 box of eggs, and 1 bag of flour each cost? How would you go about solving this problem? We can state this problem mathematically in terms of a system of linear equations. The unknown variables correspond to what we are trying to find out, the cost of the base amount of each product. Each one of the equations is linear, because the customers buy a multiple of the base amount of each product, a multiple of each unknown. And putting the equations which each represent a customer together, we get a system of linear equations, which contains all of the relevant information given in our problem. See if you can translate the problem from its current text form to a system of linear equations. I'll give you some time to pause and think about it. In this case, the relevant information includes the amount of products each customer purchases, as well as the total price paid by each customer. Adding the prices paid for each individual product, we get the total amount of money a customer spends. The unknowns are the prices of the base amounts of the products, the price of 1 carton of milk, and so on. Let's call them X, Y, and Z. After replacing the prices paid for each product with the amount purchased of that product, multiplied by the corresponding unknown, the price of the base amount of that product, our system of linear equations is now complete. We have our system of linear equations. What do we do with it? We solve it. And with we, I of course mean you. Once again, try to solve it yourself before I explain how it's done. I'll give you some time to pause and think about it. With each one of these equations, we can solve for any of the variables, but after doing so, the right side of the equation will still contain variables, which won't let us determine the concrete numeric value of the variable we solved for. So what we really want is a so-called trivial equation, an equation of the form ax equals b. That way, we can simply divide both sides by a and get a solution for x. By scaling equations and adding them together, we can strategically eliminate variables to hopefully end up with a trivial equation. So let's go ahead and do exactly that. First, we will start by getting rid of x in the second and third equations. To do that, we will multiply the first equation by -1 to negate all parts of it. Then, we can add it to the third equation. -3x plus 3x is 0, so the x term in there cancels out. To also eliminate x in the second equation, we'll scale the first one by 2 and add it to the second equation. -6x plus 6x is 0, so again, x cancels out. Lastly, we'll also eliminate y in the third equation. To do that, let's multiply the second equation by -2 and add it to the third equation. The third equation is now trivial, it only contains a single variable. As mentioned earlier, we can easily solve it by dividing by 2, which leaves us with z on one side and 4 on the other. Now that we know the value of z, we can simply replace the z term in the first and second equations. -4z becomes -4 times 4, and -2z becomes -2 times 4. Rearranging a little, we have now eliminated z from the first and second equations. By doing so, the second equation is now also trivial. Dividing by -4, we get that y is equal to 3. Just like we did with z, we can now replace the y term in the first equation. -2y becomes -2 times 3, and after rearranging, we know that -6x is equal to -30. Lastly, we'll divide by -6 to finally find the value of x. And there we have it. Our system of linear equations has now been fully solved. What we have just done here is no different from Gaussian elimination, an algorithm used to solve systems of linear equations with any number of unknowns. So let's recap the key steps necessary to solve any system of linear equations, not just this one. We scaled equations and added them together to eliminate several variables in order to determine the numeric value of one of their variables, insert it into the other equations, and repeat until we have a solution for each of the unknowns. We are lucky that this particular problem turned out to have a solution, but as it often is in math, that may not always be the case. We could have gotten no solutions at all, or even infinitely many. Let's have a look at two alternate versions of our initial problem to see what exactly that would look like. First, we'll explore what solving a system of linear equations with no solutions looks like. A system of linear equations has no solutions when there is a contradiction between two of its equations. For example, if the second customer had bought 3 cartons of milk, 1 box of eggs, 2 bags of flour, and paid $27, we can clearly see that there is a contradiction between the first and second equations. The second customer buys the exact same things as the first customer, yet pays $1 more, which obviously is not possible. Secondly, a system of linear equations may have infinitely many solutions. For example, if the second customer had bought 6 cartons of milk, 2 boxes of eggs, 4 bags of flour, and paid $52, he would have bought an exact multiple of what the first customer buys. That means that the second equation is simply a scaled version of the first equation, in this case by 2. If we try to eliminate the x term in it by scaling the first equation by a -2 and adding it to the second equation, the whole equation would cancel out and we would be left with 0 equals 0. Whenever you end up with an equation like 0 equals 0 or x equals x, it means that the system of linear equations has infinitely many solutions. We have an algorithm, we know what its possible outcomes are. What is there left to do? We need to generalize. In this case, that generalization looks like asking the question how this process could be applied if we had 4 equations and 4 unknowns, or 5 equations and 5 unknowns, or a number of equations and unknowns for that matter. Coming back to our initial problem from the start of the video, that would look like more customers buying more product. So let's imagine a 4th customer and cereal as the 4th product. This is what the new system of linear equations looks like. And as you might have guessed by now, I want you to try and solve it. I promise, it really isn't that hard. The key idea remains the same, nothing has changed about that, we are just doing everything on a larger scale. As we did before, we need to eliminate several of the variables. In particular, all variables below and to the left of the staircase shape need to be eliminated. This time there are quite a few more operations which need to be done, so I'll spare you the details. After all variables have been eliminated, the 4th equation becomes trivial and we can easily find its value. Afterwards, we do the exact same thing as we did earlier. Replace all occurrences of the variable whose value we just found out with that value, rearrange, solve the new trivial equation, and repeat. And that's how you solve any system of linear equations. If you want to, try your hands at these ones on the screen right now. I'll show the solutions in a few seconds, so make sure to pause right now if you want to give it a try.